Hi everybody, welcome to the lesson on regression assumptions. So let me start by telling you where we're headed with this and why we're spending an entire day talking about assumptions of regression. So Thursday we're going to be building our model, and model building is somewhat of a messy process, and it's based on a lot of information. And by the way, when we say regression model, what we mean is, what does that equation look like? Which variables are in it? And then for the variables that are in it, are they, just regular linear, or are we going to square some of them or take the square root of some of them? That's the kind of thing that we're going to have to decide. And so there's a lot of information that goes into that. And we've already seen some of that when we looked at which variables are statistically significant. But regression comes with a whole set of assumptions, and we need to try to meet those assumptions as best we can. With the regression assumptions, if there are assumptions that are not met, we could and sometimes should try to do something called remediation, which is how we fix it so that the assumption is met. So what do we do? How do we change the model to make sure that the assumption is met? So that's what we're going to be talking about in today's lesson. They're also called diagnostics because, these are the things you check to see if you need to change things in your model. All right. So we're going to spend the entire day just talking about what the regression assumptions are, and then what are some possible things you can do. We're going to look at these just one at a time, and then on Thursday we're going to pull it all together and talk about what the process looks like of actually, doing all this and coming up with a final model. So to get started, a lot of these assumptions have to do with the residuals. So I wanted to take just a minute to remind you what the residuals are. Those are the distances above or below the regression line of all the observations in the data set. So the residuals are denoted E sub I, and they're calculated as the actual data point minus the predicted data point. Okay, and there's a full explanation of that, including a graph in the lecture notes from last class. So I would encourage you to look at that for a full review of it. So there are 7 regression assumptions we're going to need to evaluate, and we're going to go through these one at a time. I just have put them all here to start with so that you can see them. We want to know that our independent variables are not highly correlated with each other. We want to make sure we've got the right model, meaning that the regression function is linear and that it includes all the necessary variables, and that it doesn't have any outliers. And then we want to know that the residuals have constant variance, that they're independent of each other, and that they follow a normal distribution. So we're going to look at all of those one at a time as we go through. And we're going to use the same example we used before with the Mecklenburg Quality of Life data set predicting property crime rate. And we're going to use 5 possible independent variables here: household income, population density, youth population, public nutrition assistance, and employment rate. So rather than going through each one of these and having to rerun the output, I went and just made a list where you can get all the output at one time to start with, and then we'll be able to refer to it as we go. To start with, we need our correlation matrix, which includes all of the independent variables, not the dependent, just the independent. So we're going to go over to our, just like we've done before, analyze, correlate, bivariate. And let's see, we said population density, youth population, household income, employment rate, and public nutrition assistance. I think that's right. I'm going to check. We said 1, 2, 3, 4, 5. Yep, those are the 5. Right, so we click OK, and that's the first piece of output. Next, we're going to run our regression function, and then this shows us 3 things we need to make sure to do while we're in there. So we're going to go to Analyze, Regression, Linear. Property crime rate is the dependent variable. And then the independent variables, you can put these in any order, it doesn't matter. Population density, youth population, household income, public nutrition assistance, and employment rate. I'm just going to make sure. Yeah. All right. So in here, under Save, we're going to want to check Unstandardized Residuals. We'll see what all of this stuff does here in a bit and how to use it. It's just for right now, I want to go ahead and get all of the SPSS output. And then under Plots, there's 2 things we want. One is Produce All Partial Plots. And then the other one is Residuals. So Z-Resid versus Z-Pred. So Z-Resid is going in the X's and Z-Pred is going in the Y's. So we'll click Continue and we'll click OK. And I will tell you now what one of those things did. Where we said Save Residuals, that's adding a variable to the data set that shows us what our residuals are for each observation. And we want to check normality on that. And that's what this is here. So the explore function with normality. So explore. Our unstandardized residuals. And under Plots, we don't need our stem and leaf or histogram, but we do want the normality plots with tests. So click OK. And we've got everything that we're going to need now. Okay, and we'll go through all of this one by one. So our first assumption is that the independent variables are not highly correlated. If they were, this would be called this is a condition called multicollinearity. A fancy term for the independent variables are highly correlated. Now, when we say highly correlated, we mean really, really highly correlated, like 0.9-ish or stronger. Okay, this is just me saying this. I don't think, I've never seen a statistician that specifically recommended a cutoff for that, but if this assumption is violated, it means that you basically have the same variable in there twice. Okay, if, for example, in our data, let's say I don't know, let's say age of residents and youth population were highly correlated. that would mean that these are basically the same variable, just measured a little differently. And that's the case whether it's highly correlated in a positive direction or in a negative direction. So if you've got two variables that are very, very highly correlated, you want to keep just one of them. Okay? And how do you decide which one? This is the first of many times well, I guess it's not the first, but this is one of many times that I'll say, rely on the context of your data. So if you have to decide between two variables, which one to keep, look at your data and see which one makes more sense as a predictor for your dependent variable. Let's look at this assumption with our data. I already copied our output over here. So our output, this was the first thing from the output, and I just went ahead and put it over here. So if we look through these correlations, all of the correlations above this diagonal, I'm not seeing any that are strong enough to be concerning. None of these, the strongest one of these is negative 0.222. In this row, the strongest one is negative 0.68. And then of these three, the strongest is negative 0.62. So we don't have any problems there. It kind of surprises me, actually, because I would expect that household income and public nutrition assistance would be very, very highly correlated, because public nutrition assistance is based on household income. But according to this data, it's not. All right, so that's our first assumption. Our second assumption is that the regression function is linear. If we're trying to use a linear regression function, but it turns out the data shouldn't be linear, it means we've picked the wrong model. So the way we evaluate this assumption is we look at scatter plots, separate scatter plots of each independent variable against the dependent variable. So if we look over here at all of these, we're looking to see if there's anything that looks nonlinear. We do have a couple of outliers up there. We've talked about that before. One of these is uptown. I'm not sure what the other one is. But there's nothing here that looks nonlinear. And what we would be looking for there is something that looks like it might be a parabola or a square root or something like that. And so if we look through these, nothing is jumping out at me as being nonlinear. Okay, and these are plots of each one of our independent variables versus the dependent variable. This is what comes out when you click over here in SPSS. When we click the partial regression plots or partial, so when we were in here under plots and we clicked produce all partial plots, that gives you all of those scatter plots at one time, which is nice if you've got a lot of variables in your model. So if we had seen something that looked nonlinear, here's what we would do. We would try a variable transformation. Okay, so if we saw something that looked like this, what we saw, ours were all flat. which actually makes it look like there's not that much of a relationship at all, which is, you know, if I'm looking at that, I might be a tiny bit nervous that nothing's going to be statistically significant. But if we see a pattern like this in our scatter plots, we might consider a transformation of X of this. And what we would do is, we're talking about replacing X in the model with the square root of X or log of X. So in our model, suppose it looked like youth population. Suppose youth population looked like this. If it looked just a little bit like this, we would do a new version of youth population where we took the square root of it. And to do that, we would do transform compute variable and something like square root youth population equals, and then SQRT and then pick our youth population variable. We'd click OK, and then that would give us the new variable. And then we would plug this into our model instead of youth population. And once we do that, then we would hope to see something that looked linear. So we would hope that that would remedy this, this pattern that we saw in the plot. If it's, like I said, if it's mildly like this, you do the square root transform. If it's strongly like this, you do the log transform. And you can do log base 10 or natural log, either one. If it looks like this, then you're going to do an x squared transform. Or if it looks a whole lot like that, you know, very strongly like that, then you're going to do an e to the x transform. And finally, if it looks like this, then you can either do a 1 over x transform or an e to the negative x transform. Be careful with all of these of the domain. You know, you can't do 1 over 0, so you'd want to make sure that you didn't have any zeros in your data. Or for the square roots, you wouldn't want to have any negatives in there. Same thing for the logs. All right. So that's what we would do there. The third assumption is that the model does not have outliers. To look at that, we're going to look at the residuals. And this is where we're going to look at the box plot of the residuals. And that is coming out with the output. We've got it. Because we ran those normality diagnostics, and this is just one specific one of those. So here's our box plot, and maybe it's bigger over here. I can make it bigger. So I think we can see here that we do have a lot of outliers on this box plot. So we have definitely violated that assumption. What's the problem with that? A couple of problems. One is that an outlier can mess up your ability to make inferences or predictions. But even more concerning is that an outlier can have a strong influence on what the model looks like. So just the way the equations work, one or two outliers can really shift the way the entire regression line looks. And you don't want to have that. So what do you do if it's violated? Well, you don't want to throw out an outlier unless you have a good reason. And so you want to look and see what happened. Why is it an outlier? If there's an error, take it out. If it's not an error, or if there's not something different in that process, if it's not fundamentally different, then leave it in. And here's a quote that says, "Sometimes outliers are bad data and should be excluded, but sometimes they're Wayne Gretzky or Michael Jordan and should be kept." So there are those unusual cases that are still legitimate and are worth analyzing. In this data, I would say, I haven't looked at what observation 285 is, where that is, but I know this 337 is uptown, and to me that's just a very different, that's not a typical neighborhood. And so that's not one that you would want to generalize to. So just my opinion, I would throw out uptown, but probably leave everything else. So the other thing you do is, sort of the gold standard is to run the regression both with and without the outlier and see how different the model is. If it doesn't make a big difference, then go ahead and leave it in. If it does make a big difference, then you got to think about it some more and decide, kind of go back to this step here and decide whether you want to keep it. There is something called robust regression, which we're not going to talk about, but I wanted to put that in there so that if you come back to your notes later, sometime in the future, you'll see that's something to consider. Our next assumption is that the residuals have constant variance. This is called homoscedasticity. This is sometimes spelled with a K instead of a C there, but regardless, it's homoscedasticity. And what that means is that we have the same amount of variance throughout the model. So here we're looking at a plot of residuals here versus predicted values of Y. And here we see homoscedasticity. There's not a pattern. We see the same amount of variability for all of the residuals. Here there's a couple of different common ways you might see heteroscedasticity, which is bad. This one's called the bow tie effect for obvious reasons, where in the middle there's not a lot of variability, but on the ends there's a lot. And then you might see something called the megaphone effect, also for obvious reasons, where on one side you've got a lot of variability, but not a lot on the other. And you can see the opposite of this may be true, where you have, a lot in the middle and not much on the ends, or the reverse of this could be true. If this assumption is violated, it means our coefficients may not be as precise as they should be. And it also means that if we want to do predictions, they may not be valid. So to evaluate this assumption, we're going to look at a plot of standardized residuals versus the predicted values. And we generated this in our regression output when we did under plots, when we did the residuals versus the predicted. And Z means it's standardized. I mean, this part isn't super important for you to know, but this just means that they're subtracting the mean of all of the residuals and dividing by the standard deviation so that they're independent of the context of the data, independent of the units of the data. That part doesn't matter. Just know that you're doing the residuals versus the predicted. So if we look at that for our data, here's our residual plot. So our residuals versus predicted. It's extremely hard to tell from this one. I think you can see this is where you get into a whole lot of judgment calls. It might be easy to look at that and say that's a megaphone effect, but it's mostly looks that way just because of these two outliers. So that one is really a judgment call. I would say that it's not off by enough to do anything about it. So speaking of what to do about it, what would we do if that's violated? Well, we might try a transformation of some of the x variables. So if we see something, and fixing that in this previous assumption. So if we see something here that's not linear and fix it, that may fix this. Or if we fix something up there, it may mess this up. So that's where things get really fun. So you could try a transformation on some of the x variables, or you could try a transformation on the y variable. You could do a natural log, a square root, or an inverse transform on your y variable. I put in here that you might look for plots of each x variable versus the residuals. That's a lot of work to look at, and in theory, I guess you should, but sometimes people are running models with, 100 variables. And you could look at that, but your eyes would probably cross in no time. At least I know mine would. SPSS doesn't have an easy way to do that, like it did with all of the individual scatter plots. So if you were doing that, you'd probably want to learn how to write a little bit of code where you wouldn't have to, click to create 100 different scatter plots. And I put in here that transformations can be used, so transformations on y can be used with transformations on x variables. So you can have in the same model a y that's been transformed and x's that have been transformed. So you can see all of the different permutations you could have, even if you just have 5 variables. Each one of those could have a transform. Each one of those could be in or out of the model. So there's a whole lot of options here for what to do. The next assumption is that the residuals are independent, but that's only a concern when we're looking at time as one of the independent variables. So we don't have to worry about that here. This is a snapshot data set, as are all of the ones we're going to look at. The next assumption is that the residuals are normally distributed. This is really only going to be an issue if you want to make inferences on your predictions. And that's something we're going to talk a little bit more about next time. When you generate your prediction, you can create a confidence interval around that prediction. So you can say, we are 95% confident that the actual prediction at this point, that the value of a new point here will be in this interval. And to have that, you really need to look at normality. Otherwise, it doesn't really matter. To evaluate it, though, we would save the residuals and run the normality diagnostics. And I've got those over here. We've got a skewness of 8.894 in our residuals, and we've got kurtosis of 110.533, which is the highest kurtosis I think I've ever seen in all the years I've been doing statistics. So this is obviously non-normal, as backed up by the Shapiro-Wilk test and the Kolmogorov. We've been doing Kolmogorov-Smirnov, not Shapiro-Wilk. That was in one of my other classes. But regardless, clearly non-normal, and you can see from the normal probability plot as well, highly non-normal. So if we wanted to do some confidence intervals on that, that would be a serious concern. All right. Finally, our last assumption is that the model includes all of the independent variables that it should have. So within the data set, that you've included the right data. So what you should do is go back and look at your data set and really think about, according to the context of the problem, what should be in the model but is not. So one thing that you should have done to start with, and I didn't mention this because it's part of model building, which we'll get into next time, is you're going to want to look at your data, and you're going to want to be kind of the expert on the data. So you're going to want to understand a little bit about how the phenomenon works. So in this case, you might want to be up on crime or up on urban dynamics or something. And you're going to look through your data and you're going to say, what would I expect to have an impact on property crime rate? And so I picked those 5 variables based on some ones that I thought might be interesting and ones I thought might be relevant. But that doesn't mean that there might not be others. So, violent crime rate might be highly correlated with property crime rate, and it might be an excellent predictor, but I would not expect that would be a cause. So I didn't put that in the model. I thought population density might be, because, the more people you have in an area, the more crime you might have. I thought the employment rate might matter. I thought that, income of the neighborhood might matter, because if they're in a wealthier area, they might be more likely to be things stolen from them. I thought that the youth population might make a difference. It's a stereotype, but I guess young people are maybe a little more likely to steal than older people. So that's why I chose the variables I did. Once you've got your model, you should look at any other independent variables and just reevaluate them. You can look at plots of those independent variables versus your residuals, but ideally you would have looked at that at the independent variables to start with. You don't want to throw everything in there at once, but you want to try to be thorough at least to start with, and then start paring down. But more about that on Thursday when we talk about model building. Basically, if you look back at your data and you see that there are other variables you might include, looking at plots of those independent variables versus the residuals, if you see a pattern there, then you might add that variable to the model. All right, so that's it for this lesson. For now, I want you to get good at evaluating all of these, and then next time we'll look at pulling all of this together to make some decisions and come up with a final model. All right,